We'll start with chapter 5 in this lecture. And the first section in chapter 5 is area and distances. So here is the definition of area. Estimating an area, the area A of the region S that lies under the graph of a continuous function is the limit of the sum of the area of approximating rectangles. Suppose I ask you to find the area of a circle. You all know it is pi r square. What if I ask you to find the area of this shaded region? You know it's half the circle, so you might say that it's pi r square divided by 2. Similarly, if I give you any other area of a known geometrical figure, it's easy to predict the area. But what suppose if I give you a geometrical figure, something like this? I have a smooth curve here, and I want to find the area below the curve. That's this area under the curve. This is not a nice, neat geometrical shape, and we are not familiar with any formula for this. So now we'll be using the area of rectangle concept, area A of a region S, to answer this question. So this area under the curve will be divided into rectangles of equal width. We all know how to calculate the area of a rectangle, and we will sum up all these area of the rectangle, and hence we can find the area under the curve. But when we do this, there is two different processes. One is called as overestimation and the other one is called as underestimation. We'll discuss about that, but let's first start with this area definition. Area A of a region S that lies under the graph of the continuous function, this is that continuous function, is the limit of sum of area of approximate rectangles. So the area formula area A is given by limit of n approaching infinity, Rn. R is the area of the rectangle. N approaching infinity, assume that we have n infinite rectangles. So the first rectangle, it's fx1 times delta x. Assuming that fx1 is the y value, which is the width of the rectangle, and delta x is the x value, which is the length of the rectangle. So delta x is here, and this height is called as fxi. So length times the width is the area of the rectangle formula. So you do this for the several rectangles. So you have fx2 del x2, fxn del xn, and so on. And finally, when we sum up all these areas, assuming we have infinite rectangles, we have a limiting condition n approaching infinity. We call this to be area under the curve. So let's do this example. Estimate an area. Use 4 rectangles to estimate the area under the parabola y equal to x square from 0 to 1. So first let's draw a parabolic curve y equal to x square. You're not drawing the curve here. You're not drawing the curve on the negative x-axis. The reason is you are asked to calculate the area under the curve when you have the x limits 0 to 1. So I'm going to mark 0 here and say 1 here, the extremity. Now before I do anything with this rectangle, let me calculate the delta x. Delta x is a small increment in the x value. And you can also call this as the width of the rectangles. So the formula to calculate the rectangle width is b minus a divided by n. B is the right extremity value, which is 1. A is the left extremity value, which is 0. N is the number of rectangles we want to divide. The question asks us to do 4 rectangles, so I'm going to write it as 4. So simplify, you can tell this as a 1/4, or you can say this is 0.25 if you want the decimal conversion. So now the question also asks us to estimate the area. This can be done in 2 different ways. One is right end point estimate, the one more is left end point estimate. So to start with, let me use the right endpoint estimate. So I'm going to write this as right endpoint estimate. So if it's right endpoint, I do consider the rightmost point 1, and I'm going to neglect the leftmost point 0. So let me start this by dividing into 4 equal with 0.25, 0.5, 0.75, and then comes 1. Let me redraw this curve a little bit so that I should be able to draw the rectangles below this curve. Okay, now you're good to write x sub 1, the first point, so x sub 1 is the first point. I'm going to name this as 0.25, then comes 0.5, 0.75, and 1. So I'm going to write x sub 1 as 0.25, x sub 2 as 0.5, x sub 3 as 0.75, and x sub 4 is 1. Now having written the x sub values, let me write the triangle rectangles here. I'm going to start with the rightmost endpoint. I'm going to draw vertical lines to 1 and vertical lines to 0.5. I want to make it look like a rectangle, so I'm going to extend this on the top and make it look like a rectangle. Similarly, I'll drop a vertical line to 0.5 and then extend it a little bit to the top and then draw the horizontal line. One more vertical line to 0.25 and then extend this line to make a rectangle. So from the origin, you go little above and again you draw a horizontal line to make a rectangle. So you're seeing some region above the curve. So all this is overestimating. So now let me write the R4 area of a rectangle formula is delta x f of x1 plus delta x f of x2 delta x fx3 plus delta x fx4. So delta x is a term which is common in all. You can factor it out. F of x1 plus f of x2 plus fx3 and then plus fx4. Delta x is a small increment in the x value, which we know that we calculated on the top. It is 0.25. Now we calculate the functional value at 0.25 because x sub 1 is 0.25. Functional value at 0.5. The functional value at 0.75 and functional value at 1. So the question is, how will you calculate these functional values? In the problem, we did trace a curve f of x equal to x square on the interval 0, 1. So you know f of x. So how do we calculate f of 0.25? Plug in x equal to 0.25, so it's 0.25 square. Similarly, how to calculate f.5? It's a functional value at some particular value 0.5. So all you do is 0.5 the square. Similarly, you can calculate the rest of the values, the functional values. So plug all those values back to the expression on the top, simplify, you get 0.46875. So when you plug these values here, you get this simplified value 0.46875. Now you can make a note here saying f of x, or let me write it as a note here. If a function is increasing, the graph we saw for y equal to x square is an increasing function graph. If the function is increasing, then the area under the curve R sub n gives an overestimate for the area under the curve A. R sub n is the area of the 4 rectangles in this example. So what suppose if I change this increasing by decreasing? Then the overestimate becomes underestimate. So what we are saying here is A will be less than the R4. For sure, area under the curve is less than the area of the 4 rectangles because we have some estimate here which lies above the rectangle, these upper area, the small rectangles which we extended to have a nice neat full rectangle, they are the ones to make an overestimate for this problem. So let's do a similar estimation using the left endpoint. So this time I am going to write left endpoint. So let me draw a curve, the same curve y equal to x square. But if I use left endpoint, I start by saying x sub 0 first, which is 0. Then I divide 0.25, 0.5, 0.75 and say 1. So if x sub 0 is 0, x sub 1 is 0.25, x2 is 0.5, x3 is 0.75. The question still says that we want 4 rectangle and we have said that we are using left endpoint, which means you're good to neglect the rightmost point 1 when you draw the rectangle. So now from here to this point you make a small rectangle here. And then you extend a line 0.25 and then again make a small rectangle here. One more line, extend, make a small rectangle. Extend, and then you make a small rectangle. Let me erase this a little bit. And let me clearly write which is the point. 25 point, 0.5, this is 0.75. So I have to draw a line to 0.5 and then here I mark the rectangle. Similarly, I draw a vertical line and I mark the rectangle area. This is your point 1 and you mark the rectangle area. So when you use the left hand point, all you see is you have area above the curve which is not considered. So you're leaving out area when you calculate area of each rectangle. So area under the curve will be L4 equals delta x. We know it's fx1, fx2, fx3, f of x4. Add them and we know x0 is 0, x1 is 0.25, x2 is 0.5 and x3 is 0.75. So plug all these values here. If you write x sub 0, x sub 1, you want to write 0, 1, 2, 3 here. The suffix value should match with the x sub values description on the top. So calculate similarly like how we did for the right end points. Simplify. you will see that this is 0.21875. So now you see that you neglected the rightmost endpoint 1. You don't plug in f at 1. At the most, you plug in f at 0.75. So now you want to make a note here. If the function is increasing, then if the function is increasing, let me write it clearly. If the function is increasing, then L sub n, which is the sum of area of rectangles, gives an underestimate for area under the curve A. So all we are saying is L sub n will be less than A. So I'm going to write this increasing as decreasing, and the underestimate becomes overestimate. So sometime we added more area in the first part of the problem, and the other time in part B of the problem we added the less area, like we were leaving out a lot of space above the rectangle. So we cannot say this is an exact area under the curve. So this is an underestimation as you're leaving out area. And you're considering extra area under calculation, you call it as an overestimate. So what suppose if we make a table and try to analyze how these values go? N, L sub n, R sub n. Suppose we have the first value, say for 10 rectangles, L sub n is 0.2850, R sub n is 3850. You're seeing an overestimate for this and an underestimate for this value. Similarly, for 20 rectangles, suppose the calculation shows that it is 0.30875 and 0.35875. Next, for 100 rectangles, 0.32835, 0.33835. One more 1000 rectangles, 0.3328335, 0.33383335. So when you carefully observe these values here in the table, as you increase the n values, the ln and the rn value are converging to a common estimate. You're seeing it's 0.3328, 0.3338. So up to 2 decimal places, you have the same values at 0.33. So now you can say that the 0.338335, the last two ones, are a good estimate if you are approximating up to 2 decimal places. So you say approximate to 2 decimal places, and you're going to write this as 0.33. So we saw two subcases, one with the overestimation and the other one is underestimation. All we are doing is calculating area under the curve by summing up the area of rectangles under the curve. Next example, estimate the area under the curve f of x equal to 7 plus 2x square from these two x limits using 3 rectangles and right endpoints. So first let's draw this curve 7 plus 2x square. If it is just x square, you know it's a parabola. You multiply by 2, so you are stretching out the parabola. You're adding a 7, so you're shifting the parabola. So a typical parabola, you're going to change it a little bit using the transformations, and the new parabola looks like this. You want this parabola from -1 all the way up to 2, so you can mark these points. And then you can see whether you have an overestimate or an underestimate. So the question also says the right endpoints, and you're using 3 rectangles. So the rightmost point is your x sub 3, x sub 2, x sub 1. So you're going to neglect the ones at -1. So if it's the rightmost point, you start by drawing the rectangles from the right. So from the curve to the point 2, draw a vertical line. And then you want to extend this with the dotted line. Similarly, from this point here, let me use a different color. You draw a vertical horizontal line, and then the vertical line is already there for you here. So again, you are overestimating when you draw one full rectangle. Whereas for this curve on the left, when you try to draw a line and then to make it as a rectangle, you see that you are underestimating. You are leaving out some area on the top. So you want to write this as S sub 1, the first rectangle, S sub 2, the second rectangle, S sub 3, the third rectangle. So this curve here is f of x equals 7 plus 2x squared. Now let me calculate delta x, which is 2 negative of -1 divided by, you want 3 rectangles, so you write 3. So simplify the numerator, 3 divided by 3, you get 1. And now start writing the area of some of the 3 rectangles are 3 delta x times fx1, fx2, fx3, and you want to add all these f of x values. So delta x is 1, f0, f1, and f2. So you know where to plug in this f of x values here, 7 plus 2x squared. Simplify and you get 41. In the next example, you are asked to improve this estimate by using 6 rectangles. So when it says 6 rectangles, you're going to change your delta x. So let's calculate it. It's b minus a divided by n. The right extremity is 2, the left extremity is -1 divided by 6 rectangles. So you have 3 divided by 6, which is 1/2. So draw the same curve, but you're going to extend the number of rectangles this time. So from the center 0, you can move on with the units of 1/2, 1, 1 1/2, which means it's a 3/2. Again, add a 1/2, it becomes 2. On the left, you want to write -1/2 and then -1. Now, you're improving your estimate by using the 6 rectangles. So the type of endpoints will not change. It's still the previous problem. You're going to do it with the right endpoint. So let me start the estimate using rightmost endpoint. From the curve, you draw a vertical line towards 2 and extend this to make look like a neat rectangle. Similarly, from the curve, draw a vertical line, extend it above to make it look like a rectangle. Again, from the curve, a vertical line, extend above to make it look like a rectangle. Here, you have already a vertical line, draw a horizontal line, and you see that you are underestimating. Same thing here, when you draw a vertical line, you're seeing you're underestimating. And same thing to the left. When you draw a vertical line and join them, you're underestimating. You can see that you are underestimating here on these 3 rectangles. The reason is the curve is decreasing. You have a decreasing pattern of the curve. Whereas you are overestimating because you are seeing an increasing pattern of the curve. So the pattern of the curve increase or decrease has something to do with underestimate or overestimate. So we know n is 6 and delta x is 0.5 for this problem, and we are using the rightmost 6 points. So start by naming the last point as xx. So the first point will be negative half, then you have x2, x3, x4 all the way up to x5. The last one is x6. Now you write area of the rectangle R6 will be delta x times fx1 plus fx2 all the way up to fx6. So plug in delta x is 0.5 as we calculated, functional value at negative half, functional value at 0, like this you keep going. The last one is functional value at 2. Simplify and you see that you get 28.75. The next one is you want to repeat the part A using the rightmost endpoints, but this time, and 3 rectangles, but you will use the midpoints. So for the midpoint, you want to come up with the delta x. So let's do that. N is 3, same as the first part of the problem, 3 rectangles. And you say delta x is 2 negative of negative 1 divided by 3, so still it's 1. So let me draw the same curve, the parabolic curve. It's decreasing here and increasing here. Negative 1, 0, 1, and then you have 2. So this time you want to draw the midpoints. So between 1 and 2, it's the midpoint here. So draw a vertical line to 2, draw a vertical line from the curve to 1. But this time draw a horizontal line towards the midpoint and then join to make a rectangle. Same thought, you want to draw a midpoint here and a vertical line dropping down from the midpoint. Then draw a horizontal line. Then you see you are overestimating on the left and underestimating on the right. Similarly, you draw the midpoint, draw the horizontal line, and then you draw this vertical line. So sometimes you're seeing an underestimate, sometimes you're seeing an overestimate. It's a combination of both when you choose the midpoints. So let me redraw this a little bit. So let's write the formula. M sub 3 equals f of x1 delta x, fx2 delta x, fx3 delta x, and name this as x sub 1, x sub 2, x sub 3. So delta x is 1, calculate the functional value at negative half, and then at half, and then at 3 halves. So this is f at 1 half and f at 3 halves. You know where to plug in the given function, and then simplify it is 13.25 times 2, which is 26.5. The next example, it's an application problem. Speedometer readings for a motorcycle at 12 seconds intervals are given in the table. You want to estimate the distance traveled by the motorcycle during the first time period using the velocities at the beginning of the time interval. If you carefully observe the t values, you have an increment of 6, 12, and again it's 12, and uniformly it's 12. So we have a nice increment of 12. So you can write delta t, it's no more delta x, but write delta t. It's b minus a divided by n, which is 60 minus 0 divided by the number of values, which is 5, and your answer is 12. Or you can read this carefully and understand that delta t is 12. Now carefully read the velocity values. You don't have a nice pattern. You have decreasing here, 30 to 22, and then again after 22 is increasing. So you have a decrease and increase pattern. So it's not like the algebraic expressions which we did in the previous examples. So now let's estimate the first part. Estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the time interval. So first you would want to draw a number line t equal to 0, 12, 24, 36, 48, 60. Then you call x1, x2, x3, x4, x5. The question says beginning of the time interval, so you want to neglect the last point. We know the formula for distance. Distance is velocity times the time. And we know that delta t in this problem is 12. So the distance will be 12 times f of x1 value, f of x1, or you can call it as f of t1 here. And then you can sum up these values, ft2, ft3, ft4, and ft5. Just to have these consistencies, you can rename this. This is the t-axis. You can rename it as t values rather than the x sub values. So all you do is plug in. You write f at 0, f at 12, f at 24, f at 36, and then f at 48. And when you simplify, you get this to be 1548 feet. In the next part of the question, you are asked to find one more estimate using the velocities at the end of the time points, which means at the rightmost point, you're going to leave out the first point. So I draw a number line T0, 12, 24, 36, 48, 60. This time I use the rightmost points, which means in this direction. So I neglect this point. And I'm going to name this as T1, T2, T3, T4, T5. So we can use this as the distance equal delta T times Ft1 Ft2 all the way up to Ft5. You know what's your T1, T2 up to Ft5. So plug in these values, simplify, you see you get 1512 feet. So now the question asks you, are your estimates in the part A and B upper or the lower estimate? So here is the answer. The beginning of the time intervals say the left endpoint, the distance what we calculated is 1548 feet. And at the end of the time interval, all we have is distance equals, and we use the rightmost endpoints, distance equals 1512 feet. So these estimates are neither underestimate, or you can say upper or lower estimate. When you say neither, you want to say this as nor. So these estimates are neither upper or nor lower, since the velocity v is neither increasing nor decreasing. So we saw in the table, the velocity v doesn't have a nice pattern, so you cannot conclude whether it's an upper estimate or a lower estimate. So in this section 5.1, we did learn about area and the distances. So we know how to calculate area under the curve. We divide the region into some number of rectangles, and then we calculate the width of the rectangle and calculate the functional values and consider whether you're choosing a right endpoint or are you choosing a left endpoint or the middle point. So we'll end this section here.